those are modeled results. What do we find when we actually do research on these types of things? These are old growth versus second growth forest soils in western Montana that we worked on. These forest floor carbon here on the vertical axis, in other words, the litter, the L, F, and H layers. And here we have several different sites, and these are each made up of five pairs at each site of old growth, never harvested, and second growth, having been harvested and replanted 40 years ago. And this is the relative carbon reaccumulation in the forest floor is significantly less than in the old growth system. In terms of the mineral soil carbon, we see no significant difference at the different sites. And in terms of ecosystem carbon as a whole, including overstory, litter, understory, and mineral soil, we see a significant difference between our second growth and our old growth. So about 3 times greater total carbon storage in our old growth, but no differences in the mineral soil carbon with just one rotation. This is an example. I had to use this one because I think I don't know if Sonatan's here today, but this is Sonatan. There you are. Worked with me in North Wales when I was there, and this is from his work showing a significant decrease when these forest plantations are harvested after about 60-year rotation, and a decrease in the O horizon carbon, but the mineral soil carbon actually being increased by the incorporation of all that litter and slash into the surface soils by disturbance. But at 8 years out, at one of the sites, he's finding a net decrease across the board. Management, forest management, directly influences stand density, and this is something we have to keep in mind. When we go back into if we don't go back into a forest that we've heavily managed, we get something really different than was there as the old growth forest, and this is part of the result of why in that other study we had so much lower carbon accumulation. The density of trees is far greater in logged than in unlogged on bird stands across all these different sites we studied in western Montana and northern Idaho. And this is burned and unlogged. Okay, so it's been experienced in its natural fire return interval and was not logged. And you note the density of trees per hectare is down around 200. These are low elevation, high, large diameter trees, and ponderosa pine and Douglas fir. And then when we go to a site that was not burned, or the pairs, across these multiple different sites that were unburned and unlogged, we have a significantly higher amount of Douglas fir. But when we go to unburned and logged, we have the highest amount of Douglas fir density, and the total density is highest in this system. So the forest density increases significantly. Now, I'm going to just take a little sidetrack and say, this is just to show, we have some new data that's coming out on this that will be much better than this. This is an older figure that shows the yellow. You won't be able to see these figures. The yellow is from 1972 to 79. Orange is from 1980 to 1989. And red is 1990 to 2002. And this just shows a shift in where forest management was done in the, these brown outlined areas were all federal land, okay, or federal land. And the timber harvest just shifted from state and federal land in the 70s, stopped being harvested and stopped being managed, and was shifted to heavy harvesting, clear cutting on private land, okay? And so the net effect is those federal lands were let sit. And that seems good from a carbon sequestration perspective. This just shows in this figure the amount of carbon released from the Industrial Revolution up until the about 1985 or 80, let's say, and the amount of carbon released in the U.S. from the forest sector. And then after the federal lands stopped being harvested at the rates that they were being harvested, which were unsustainable, we start storing carbon, okay? But these non-managed forests, the ones that are not managed, are depending on the ecosystem that we're talking about. This is hemlock and Douglas fir. The hemlock grows so incredibly fast on the west side of the Cascades that it just fills in and ends up out-competing the Douglas fir. This is a stand that never had its pre-commercial thinning. This is a stand of Douglas fir and ponderosa pine, where the Douglas fir outgrew the ponderosa pine, which was mostly cut out of the system. And the net effect is we don't end up supporting species of concern. We don't end up having the condition of habitat that we hope for, and we have slow recovery of the soil ecosystem as well. Okay, I'm going to shift gears now and hop into the boreal and talk just a little bit about boreal forests. And when we start thinking about, can we add more carbon to boreal? The boreal accounts for about 1/3 of the world's soil carbon, yet it's only about 17% of the landmass, terrestrial landmass. So, and most of it is below ground. We have to keep in mind that the expansion of boreal forests into these glacial landscapes put away on the order of 500 to 1,300 petagrams of carbon in that 10,000 year period, most of it being stored beneath ground. Turnikai now estimates that boreal or circumpolar region accounting for more like about 1,700 petagrams of carbons in the permafrost and wetland soils. But these soils contain an enormous amount of carbon, and our concern is probably going to need to be more about the loss of carbon from those soils. So if we look at the circumpolar region, these, and specifically throughout Canada and Alaska and Eurasia, we have these enormous landscapes of permafrost, continuous and discontinuous permafrost soils that hold absurd amounts of carbon, and also in our histosols and our glacials. This just shows poorly drained permafrost soils on the far right. This is running on a juice here, and then poorly drained soils. We see that the huge amounts of carbon being stored below ground in our permafrost soils. The concern is what happens when a sink becomes a source. And this is really a concern with permafrost melting, and we know that. Yet in the IPCC report, the last IPCC report, they emphasize the carbon accumulation of biomass growing, forest biomass and shrub biomass growing on permafrost soils as it melts out. This guy, Coven, published a study a couple of years ago showing here on the left-hand side, without considering the melting of permafrost, on the right-hand side, the melting of permafrost. This is grams of carbon per meter squared per year, and you can see the types of the level of carbon emissions that are going to be associated with melting of permafrost are extremely high. He estimates that by 2100, about 62 petagrams would have been lost to thawing, about 7 years of our current rates of fossil fuel consumption. What about fire? Well, we know fire occurrence is increasing in the West. We have, since 1986, U.S. fire seasons about 78 days longer, 4-time increase in fire size over 600 hectares, and about a 6-fold increase in the number of acres that are burned. And that's mostly in our forests that are over 2,100 meters, which would be predominantly lodgepole pine systems. Similarly, this figure from Soya showing a gradual increase in the area burned throughout Canada and Alaska and over time. And Turetsky's figure for looking at the depth of the forest floor consumption with increasing fire size. So we have some concerns to consider with loss of carbon from our boreal systems with increasing fire occurrence in a warming climate. I think I won't spend much time on this except to say that we have high rates of carbon emissions in the US from our Alaskan boreal forest fires. And look at the error bar associated with that, though. It's variable from year to year. Otherwise, across the rest of the US, fossil fuel emissions greatly outpace the emissions associated with fires, even in fire-prone states across the West. What about the excessive occurrence of fire, excessive use of fire? In this case, I just give this as an interesting example. If we have increasing occurrence of fire, this was in northern Sweden. This is an ecosystem, these spruce cladina forests, which are different from the ones in northern Canada in that these are, well, they are thought to be, these are Norway spruce for starters, but they are thought to be a naturally occurring ecosystem. Based on pollen records, we find that it is associated with Sami burning of these landscapes to maintain open cladina forests for reindeer grazing. These are their paired counterparts, and this ecosystem has stalled out and will not recover as a Scots pine Norway spruce ecosystem as it was. Rather, it remains in this open stand structure, and I'd go into more detail on it, but it would take a little bit of time. And I'll just say that this is total carbon in the system in the O horizon. These are the reference forests versus the reindeer, lichen, spruce forests in terms of just total carbon in the O horizon. Charcoal is an interesting byproduct of fire. It is not produced in large quantities, but it is highly recalcitrant to decomposition and represents an immediate forming of passive carbon. When we have, when Dr. Lau was talking about humus formation, he didn't talk about time frame for humus formation. It's a tortuous process for accumulating. If you take biomass and look at about 3% of that actually being converted to humus, it's a long and tortuous process. Fire generates immediately in the form of charcoal, a passive part of the soil, mineral soil carbon pool. This is from a student of mine currently, Melissa Pingree, and it just shows that most of the carbon that's generated in a fire is found here in the O horizon, where in these post-fire, if we go looking for charcoal in the subsurface or mineral soil, we see that these green circles are the unburned system versus the burned, and we actually have no significant difference in the charcoal accumulation in our mineral soil between burned and unburned. Excuse me, this is unburned on the far left. My pointer is worn out, and unburned on the far right, thinned and burned in prescribed fire, and then wildfire on the far left. And this just shows the amount of charcoal carbon generated based on the amount of woody materials consumed in a fire event, and it ranges from about 1 to 8% of the carbon is converted to charcoal, of the biomass is actually converted to charcoal, probably closer to 1 to 3%. So it's similar to humus formation, but it is instantaneous. So warming's definitely going to increase the occurrence of fire. Fire consumes about 20 to 30% of the forest the forest carbon total. Soil organic matter, mineral soil organic matter isn't greatly influenced, but and regeneration after fire recaptures much of the biomass carbon loss. So fire is a natural part of that system, and we shouldn't be dwelling too much on it, but with an increase in fire occurrence and fire frequency, we could run into problems with loss of soil organic matter and specifically nitrogen over time.